Yes, we know something. So last time we stopped here basically when we found using we defined basically three main properties of a good estimator. We say that an estimator, a good financial estimator is different than the estimate. When you have certain number of samples, you can calculate an estimate using an equation called an estimator. So every time you have several samples, you do this calculation, you get new question. So basically, the estimator itself is a random value that gives you the correct value plus or minus something. And in order to understand the behavior of this estimator, we need to understand how basically the statistics of this estimator. And because of that, we defined different properties of a good estimator. We said that a good estimator ايش لازم يكون؟ unbiased, because when we do this sampling and we calculate the estimate every time, we will have different estimates, right? Now we know that the average of these estimates is close to the two values that you are trying to estimate. So first of all, it's unbiased. The second, if you look at different estimates, different estimators, different ways to estimate the same parameter, we have many ways. As we illustrated in this example, we have here four ways at least, and you can create your own. Here we have 4 ways. So every one of them will give you a random value, probably biased or unbiased, and it will give you a value. So basically, this random variable has a mean and average, which we hope that it's close to the two in the unbiasedness property. And we hope that it has a small variance. And we call this property as the minimum variance unbiased estimate. And the last property that we studied last time is that, okay, if we look at this variance and we compare it with the number of samples, as the number of samples increases, we hope that this variance of the estimator, which is the variance. So the number of samples, what do you hope for the estimator variance? This smaller, this one. So basically, it becomes closer and closer, more concentrated around the true value we'd like to estimate. And we call this property consistency. Or consistent, an estimator that behaves like this is a consistent estimator, where the variance of the estimator goes to 0 as n goes to 1. And then we stop basically up to here. Now, if we have a signal that we are trying to estimate its power or variance, then the estimator of the power will be 1 over n summation of every sample. Very similar to what we did in the mean, the estimator of the mean. However, we have x squared. However, the estimator for the variance is the interesting part, where in order to have a consistent estimator, or sorry, an unbiased estimator, you need to take every sample minus the هذا ايش نسميه هذا؟ mean estimate, right? So basically, because you don't have the true mean, you cannot subtract the true mean. If you have 10 samples, what you can calculate is an estimate of the mean. But in order to calculate the variance equation is every sample minus the true mean. We have the true mean. We don't have it because that the only thing that we can have is the estimated mean. So we subtract every sample minus the estimated mean. Now, when we do this, you need to divide by 1 over n minus 1, not 1 over n. If you divide by 1 over n, it will be biased. So if you divide by 1 over n, it will be a biased estimate. Okay, so basically, if you calculate the average of this, if you have 1 over n and calculate the average of this estimator, you will get biased estimate. And the proof of this is basically, I added it to the last slide. طيب. So that's واضح يا شباب. When you estimate, when you have certain number of samples and you'd like to estimate the mean, you estimate the mean. However, we'd like to estimate the variance, you need to subtract the true value, the true mean, which we don't have. So the only thing that you can have is to subtract the estimated mean. And when you do that, you need to divide by لاحظوا هذه اللي هي 1 over n naught over 2, 1 over n sorry n naught to make unbiased estimate. واضح؟ أي سؤال شباب؟ Let's have an example. So here we have certain number of samples, 0.1, 0.4, whatever, and we are given basically the 11 samples for a random variable, voltage source, and we know that the mean is 4 and the variance is 16. So in real life, we will not be able to find this. So now, if we use these samples to estimate the mean and the variance using the method that we did, let's see how far we are from the two. So let's see here. If we estimate the mean, this is the estimate, right? We sum all values, divide by 8. And when you do this, we get basically 3.97. And what is the true mean? So basically, it's not very far. Now, if you estimate the variance, you don't have access to the mean, the predicted mean. So what you need to do is you need to subtract the estimated mean. Okay, the estimated mean, and when you do this, you will get 14.75 instead of 16, which is a little bit more. Now I'll give you another set of samples. Basically, you have different values. Every time you have different set of values, and we hope that these estimates, the average of these 10 estimates, will give you true average and performance because they are unbiased. Right. So basically, this basically covers what we want to talk about the definition of point estimator and how we do it, and what are the good properties of an estimator: unbiasedness, consistency, and the minimum variance. Now we'll talk about one thematic method to find these estimators. Then until now, we are only relying on our understanding of the data. يعني لما اتكلمنا عن mean estimate, basically 1 over n and the sum over all the how we do it. There's an understanding that the average of certain numbers is the summation divided by n. صح? And we did other examples. Basically, it was we were relying on our knowledge. However, there was no systematic way to do this. One of the systematic ways to find a good estimator, and you see that it's good estimator means that it's unbiased and it's minimum variance, is what we call maximum likelihood estimate. MLE. This is very method and it's very systematic. الطريقة التالي, we assume that we have certain observations that are IID. IID means identify and they have the joint PDF, which is basically given by this, and we have this parameter to be estimated. So I simplified it for one parameter. So with theta 1 is an unknown parameter. Unknown parameter. Can I go with the average of the samples, the value of the samples, the edge of the maximum of an uniform distribution, the average of an exponential distribution, whatever. So this parameter is something that we would like to estimate using these samples. And we know the PDF of this. So basically, we have some knowledge on the general underlying PDF. We have some knowledge. We know that it's normal distribution. We don't know the mean and the variance, but we know it's normal distribution. We know it's exponential distribution. We don't know the average. We know that it's uniform. However, we don't know the maximum and the minimum. So we know the shape of the distribution. We know the equation of the distribution, but we don't know the parameters, the detailed parameters. Now this function has fx of x1, x2 up to xn, and theta 1, which is the parameter that we'd like to estimate, is called the likelihood function of theta. Now, the way basically the MLE estimator or maximum likelihood estimator works is the following. It estimates the estimator for theta 1. It will estimate it as theta 1 hat if this likelihood function for theta 1 hat is larger than for theta 1 or any other or theta. Basically, it's a maximization problem. So simply, you need to find the theta 1 value that makes this function. Okay. Maximum or minimum? you know the maximum. It's maximum likelihood, huh? So basically, this is the likelihood function. We'd like to find theta 1 such that the likelihood function is maximum. And for example, it will be more clear. So let's assume, or in this example, that we have random samples, x1 through xn, random samples from exponential distribution. So we know the underlying, the key concept of maximum likelihood distribution is that we know the underlying distribution. At least you know the shape of it. You don't know the details. So basically, you, from exponential distribution with parameter lambda. Lambda we don't know. lambda هو اللي تذكر exponential distribution كيف كان شكله؟ كان كذا شكله صح؟ PDF of x PDF of x right? It looks like this exponential distribution. And the plus equal lambda e to minus lambda x or مرات كنا نكتبها 1 over b e to minus x over b نفس الشيء بس هنا basically lambda equals 1 over b. Okay, so the example is we would like to estimate this parameter lambda, which is 1 over b. Lambda here is equal to 1 over b. Let's check what was b equal to. B was the average lambda. B was the average of this distribution. So, in order to do this, we write the likelihood function. What is the likelihood function? It's the PDF of x1 and x2 and x3. It's the joint PDF. What is the joint PDF of x1 and x2? They are IID. What does it mean? It means that the joint PDF equals what? They are independent. How to write the joint PDF of x1 and x2 and so on? The product, right, of the PDF of x1 multiplied by the PDF of x2 and so on. So basically, this is equal to f of x1, x1, right, multiplied by f of x2, x2, and so on, right? And because they are identical, sorry, before we go into identical, so this is basically lambda. The PDF of the first x1 is exponential. With parameter lambda, we don't know lambda. So it's lambda e to minus lambda x1, right? This is the first PDF. The second PDF is lambda e to minus lambda x2. So this is the joint PDF. All of them depend on x1. أول واحدة depend on x1, ثانية depend on x2, ثالثة x3, and so on. However, all of them depend on lambda. So what we need to find is what is lambda that makes this function maximum. How to find the maximum of function? We take the derivative and weight it, right? So basically, in order to do this, another e to minus and so on. So it's easier to take the len. If you take the len, it will be all the lens of lambda will be added together. So basically, this will be a constant n len lambda because we have len lambda plus len lambda, right? When these are the product. When you take the len, the lens will be added. So we have n lambda, n len lambda minus lambda summation of x1, x2, x3. We did not do much here. We only took the len of this function. Okay. Now, taking the len, we move on to find the derivative and equate it to 0. So when you differentiate this with respect to lambda, what do you get? Where is lambda here, Shura? Differentiating the first part, what do you get? N over lambda. And differentiating this, what do you get? Summation, right? Lambda is here, it will be the summation. So, and you equate this to 0. So basically, 1 over lambda, n over lambda minus summation equal to 0. So n over lambda will be equal to the summation, right? Which means that lambda will be equal to n divided by the summation. And we call this as lambda hat. ايش كانت lambda معناها? What did we say lambda equal to? 1 over b, right? What was b? B was the average. Yes, B was the expected value of x. So لو تلاحظوا هنا lambda is n over this, which is 1 over b, which means that
V hat, which means that V hat is what is what? Summation over N, right? Which is the same as we did اللي كانت بال binomial. So basically, this is an estimate of what? Of the average of an exponential distribution. We did it very systematically, without guessing or without using some understand ideas from our understanding. No, it's very systematic. واضح شباب how did we do it? Have another example? طيب, another example is about, again, here we have these x's, 1 to n, are random samples, IID again. However, now from normal distribution. So we know that the sum is coming from normal distribution. Our task is to find an estimate of the average and the variance. So in order to do this, so basically the unknowns here, so basically we write the PDFs, the joint PDF, with the unknowns mu and variance. These are to be estimated. هذا الشيئين. Okay. Now how do we do it? Do this? We write the joint PDF of these x's. What is the joint PDF of IID random normal distributed random? Gaussian. However, we have IID. So what is the joint distribution? Again, it's the first PDF, Gaussian, with mu and variance, sigma square, multiplied by another thing. So basically, it will be the first PDF, which is a Gaussian, with mu and variance sigma square, and multiplied by another one similar, however, only x2 will be, and so on until we get the last one, with the xn, the same parameter, mu and sigma square. Okay. Now, you can notice here that, so basically, this is the joint PDF, not this is what we know from the product that we discussed. So just writing them together, this would be to the power n over 2, and they will be exponential of some summation